Hello physics. Alright, this is the video that I promised you guys before the next lab report was due to help with the error analysis portion of your lab report. Now, we talked about this for the people who were in class. We talked about this on Wednesday, I think. And I completely forgot to record this video after school, so I'm doing it this morning instead. Now, there are more types of errors than these five, but these five are some of the more common ones that you're going to have to deal with. Now, one of the things that I said in writing a lab report in your error analysis is that you can't use the same error type multiple times. I'm referring to these. So if you say friction is a source of error in this experiment, you can't say friction in multiple places and call it three different errors. Friction is one type of error, and then you'd have to find two others for the other. Now, there is a sixth one here that I will talk about. Hopefully I won't forget. That's a little different. Only one, I know one group has run into this. But I want to explain these first before we really get into that. So, friction is pretty obvious. It's the error I think we're all the most familiar with. I'm going to use our explosions and collisions lab as an example for friction. So, one of the friction errors is that the cart, because of the friction that's on it, is constantly slowing down. Now, when we are doing momentum calculations, we are making the assumption that energy is not leaving the system except for what's caused to leave by the actual collision. So, as the cart is moving, if it's slowing down, then it's losing energy. It's losing energy because of the friction between the cart and the track that it's driving on. So as it slows down, it loses energy. That increases our error. This is one reason why it's really important to have the photo gates really close together, because the longer that they have to travel, the longer that the carts travel, the more energy is going to be lost and the higher your error is going to be. But the closer together you get them, other issues start to come up. So that's one example of friction. Another example of friction would be on the force tables experiment. We had that little target in the center of the table, and that target had to move around as you balanced the three or four hanging masses. There is just a small amount of friction between the target and the table itself. And you can see that if you make small adjustments to the masses, you'll adjust the masses, and it's not immediate that the target moves. You'll adjust the mass, and then a second later, the target will shift. That's because of the friction between the target and the table. If that friction is large enough compared to the force you're applying, then it will actually not move, even though you've come up with a more accurate possible force. So, or a more accurate mass. So that would be another spot where friction would be an issue. Whenever we use these carts, now this is not a great example of friction. This won't work with my black, I'll hold it up here. Another example of friction, and this is true for both the carts and the pulleys, is the axle assembly. I don't know if you can see it, but maybe you can hear it. This wheel is spinning, but it's slowing down. Okay, and as it slows down, that indicates that it's losing energy. That energy is being lost because of the friction in the axle assembly that holds the wheels on the cart. So there is friction there. Now, that's not a huge source of error in this. It's a larger source for the cart than it is for the pulleys from the friction lab. Our pulleys have a really, really low friction. If you spin them, they will spin for almost 2 or 3 minutes before they come to rest. Well, the good ones will. Some of them will only spin for a minute. So, but those are all examples of friction. So, in your error analysis, you would say error friction, and then underneath friction, you would list, for example, the explosions and collisions, the axle assembly of the cart, the between the cart and the track, and you would explain what the risk or what issues those bring about in the lab. Both of them cause the same issue, and that's the cart slowing down, the cart losing energy over the course of the experiment when we really don't want the energy of the cart to be changing. And there are lots of different examples of friction. Anytime something is moving, there's going to be friction somewhere. So that is always something for you to keep an eye on. Now, human error is a dangerous error to fall back on. Okay, there are times when human error is the largest error in the experiment. And there are times when human error is a cop-out that people are using because they can't come up with a better error to use. Some examples of when human error is a significant error. When you are taking a measurement, sometimes, especially with a ruler or a meter stick, human error can be a little more significant in that area. When we do our 2 sound labs, or rather 1 sound lab, 1 wave lab, our labs for chapters 13 and 14, human error is one of the largest sources of error in both of those because you have to make very, very precise measurements and adjustments, and you have to eyeball what's going on in order to confirm that everything is set up correctly. And you're making minute adjustments between trials. So human error is a significant issue there. Human error is when the human is the failure point. Okay? So if you're relying on your eye to take a measurement and that whole lab is built around that specific measurement, then human error is going to be a significant source of error. But if it's just, oh, this one number, when I took the temperature and then I measured everything else with the computer, human error is not going to be significant depending on how good that experiment is set up. So be careful falling back on human error. We do have several where human error is a serious issue. And human error is one I'm usually pretty good about. If you ask me, I will tell you human error is a big issue in this lab, or human error is not a big issue in this lab, and then leave you to figure out where the human error is a big issue. So that you're not constantly trying to guess, is this one where I can use human error, or is this one where I'm going to lose points for doing it? So you can ask on this one, and I'm not going to hesitate to tell you whether this is present. Now, I may have to go, is that a significant error, or is that a minor error? That may take me a second, depending on the lab. Now, precision and accuracy is something that I want to explain the difference between real quick. So I'm going to pause this, put a couple pictures up here, and kind of explain the difference between precision and accuracy, because most people don't know. So I will be back momentarily for you, minutely for me, I guess. All right. So for the sake of this discussion, let's pretend that these are both the same size and shape. But these are meant to be archery targets, and the crosses, or the X's, are supposed to be where the arrows have hit. So both have received 5 shots. The one at the top has a cluster, but it's off-center, while the one on the bottom is more spread out, but the average is closer to being... I'm pointing in the wrong spot. There we go. The average is closer to being in the center, whereas this average is way up here on the side. Okay, one of these would be considered to be precise, while the other one would be accurate. Precision is consistency. Accuracy is correctness. So this one would be accurate but imprecise because they're spread out all over the target. But the average tends to be pretty close to the correct answer or the correct target. While this one up here is precise but not accurate, because accurate would put it here in the center of the target, but it is a tight cluster. So they are consistent with their shooting. So if your numbers are all the same, but they're not where they should be, that would be precision. If your numbers are kind of all over the place, but their average comes out to be really close to what you're after, that would be accurate. Ideally, you want both. Precision is preferred over accuracy, though, because once you get an experiment that is precise, you can usually fine-tune it to also make it accurate. So precision is more important than accuracy if you ever have to choose. So my alarm is about to go off. So I'm going to pause this, go dismiss the alarm, and then I'll come back and finish this. Okay, so let's talk about precision errors and accuracy errors in experimentation. So think back to the force tables lab, vector addition, where you were trying to add masses to the hangers until the target was sitting perfectly in the center. Every once in a while, and I think everybody actually encountered this, you ran into a point where you couldn't quite get it to center correctly when you were putting the masses on. So if you added the half-gram mass, it would either pull it too far off target or it wouldn't be enough to get it in target. So if you put it on, it would pull it past the equilibrium spot, but if you took it off, it shifted the other way past the equilibrium spot. And so what you kind of wound up doing was choosing which one of the two was closer to what you wanted, but neither was really ideal. That would be an example of a precision issue, because we don't have masses small enough for you to make the adjustment that you need for that experiment to get ideal results. So that's something you have no control over. You can't, I mean, I guess you could take a piece of paper and cut it up and hang that on there, but then you'd have to get the mass of the paper, and that's just not something we're going to mess with in here. I just dropped the mass. So because these are not precise enough, because these aren't cut small enough, we can't do, or we can't get any more accurate in our data. So the lack of precision in these, I'm sorry, I've been mixing my words up. Because these aren't small enough, that's an accuracy error. Because we can't get the accurate answer, because these aren't small enough. Precision would be stating that this half-gram mass is more or less than this half-gram mass. This one's 4.9, and this one over here is 5.1. That would be a precision issue that you have no control over. I'm going to tell you that's not an issue with these mass sets. That's an issue that you're probably not going to see very often in this class. The exception to that is the ballistic pendulum. Sometimes the ballistic pendulums are all over the place with their data. You get a height of 2 centimeters on one trial and a height of 3.5 centimeters on another trial, and so your data is really spread out, so it's imprecise, but you still wind up usually with the average coming out pretty close to accurate. So that would be an example of a precision error, but I don't think anybody had that issue with this setup because the ballistic pendulum that you guys used was pretty consistent. I think one group even got the exact same height on all 5 of their trials. So that's definitely not going to be a precision issue. So we've done accuracy, precision, human, and friction. The next one is environmental. Now, one of you actually brought this up. This is not one that I actually recall. When one of the groups was trying to use the triple beam balances, the air from the air conditioner or the fans was blowing, and it was actually causing the balance to fluctuate while they were trying to get it to set properly. That is an environmental issue, okay? And that would be a source of error. If that meant that it never settled and you had to take a guess as to whether it was centered properly or not, that would be an environmental error. That's something that you did not have much control over that possibly injected error into your results, that made your masses inaccurate and therefore threw off all of your momentum calculations. So that's what we're talking about with an environmental error. Now, the 6th error type that was brought up, and I'm not sure how legitimate I would call this, because usually this is going to be something, well, I'll tell you what it is first. It's a hardware error, where the hardware is not functioning properly, and so you can't get accurate data. This is one with the second ballistic pendulum apparatus. I think you guys all saw this, even if you didn't all experience it. The second ballistic pendulum apparatus had a bent rod. So the pendulum, the rod that the bob was on, was bent slightly. And so because of that, the bullet would never go into the pendulum properly, or it would rarely go into the pendulum properly. And even if it did go in properly, the pendulum was bouncing back and forth while it swung up into to lock into place. And so there was a lot of noise, energy noise in that experiment, and so the data was just absolute crap. That would be a hardware error, because there's nothing you can do about that except replace the hardware. Now, the reason I say I'm not sure this is a legit error is because you can fix this. You replace the hardware, which is what we did for the group that ran into this. They swapped out their ballistic pendulum, and then they were fine. The second apparatus worked the way it was supposed to. So that's why I'm a little iffy on a hardware error. Now, it's possible if we don't have enough pieces of hardware, and one of them stops working properly while we're performing the experiment, that one of you might run into this later on. And that would be something where we'd have to address that at the time. But hopefully I would be able to actually get you better hardware for that. But I don't think I forgot anything. Those of you who were in class, if you see anything that I did forget, please let me know, and I will add it to the description of this video so that people can, so that that information is out there as well. Less than 20 minutes, that's not bad. I will see you guys all later. Hope you have a wonderful day. I guess I'll see you in a couple of hours in class. So, bye.